Silence. Then the roar of 8 Pratt & Whitney engines tearing through desert heat at 420 knots, June 7, 1981, 100 feet above Iraqi sand. Fuel gauges dropping toward empty with every passing minute. Ahead beneath 5 feet of reinforced concrete Iraq's pathway to nuclear weapons. This is the story of 8 fighter jets that flew a mission their fuel tank said was impossible. Strike so precise it destroyed a reactor dome in 90 seconds. And a tactical success that might have created the very threat it was meant to prevent. Welcome to Shadowworks. Let me show you what kept. Israeli intelligence analysts awake in the spring of 1981, 17 kilometers southeast of Baghdad. Rising from the Iraqi desert like a concrete monument to ambition, sat the Osirak nuclear reactor, officially Tammuz 1. To the French engineers who built it, a 40-megawatt research facility. To Israeli targeting officers, Hotel Tango 1, the first step toward an Islamic bomb. The reactor itself was an Osiris-class pool-type design. Picture a massive swimming pool with a nuclear core suspended in the center. Water serves as both coolant and neutron moderator. Inherently safe, entirely civilian in purpose. That's what Iraq told the International Atomic Energy Agency. Here's what Israeli intelligence photographed through reconnaissance satellites. Hot cells for plutonium extraction, no civilian justification. Reprocessing facilities, no research requirement. 72 kilograms of weapons-grade uranium. Enough for multiple reactor cores or multiple warheads. The reactor dome, 90 feet in diameter, 5 feet of reinforced concrete at the apex, designed to contain radiation, never intended to stop a Mark 84 bomb traveling at 600 feet per second. But here's the countdown that drove everything else. July 1981. Reactor goes critical. Gets loaded with radioactive fuel. After that date, any attack becomes impossible. Strike a fueled reactor, and you don't destroy Iraq's nuclear program, you create Chernobyl in downtown Baghdad. Civilian casualties in the tens of thousands. Radioactive contamination across 3 countries. Israel had exactly 1 chance to do this. The clock was already running. Iranian F-4 Phantoms had tried in September 1980. They damaged the facility but failed to destroy it. Iraq simply accelerated construction, added more concrete, increased security. The window was closing. And when it shut, a nuclear-armed Iraq, led by Saddam Hussein, technically at war with Israel, would fundamentally reset Middle Eastern power dynamics. Diplomatic efforts had failed. Economic pressure had failed. Which left 8 F-16 Fighting Falcons, 16 2,000-pound bombs. It's in a fuel calculation that said barely possible when military planners wanted to hear guaranteed success. Now let me tell you why the F-16 was the only aircraft in Israel's inventory that could execute this mission. Because this wasn't about speed or stealth or sophistication. This was about physics, fuel, and whether 8 lightweight fighters could fly farther than their designers ever intended. The F-16 Fighting Falcon represented a revolution disguised as a budget fighter. While the U.S. Air Force was building the F-14 Tomcat and F-15 Eagle massive, expensive, twin-engine air superiority platforms, a group of engineers asked a subversive question. What if smaller was better? The lightweight fighter program challenged everything. 31-foot wingspan, 49 feet long, empty weight, 16,000 pounds, about 60% of an F-4 Phantom's frontal area. But here's where it gets interesting. Same engine as the F-15 Eagle, the Pratt & Whitney. F-1 new PW200, 23,840 pounds of thrust on full afterburner. The F-15 needed TWO of these engines. The F-16 made do with one. Why? Because the F-16 weighed half as much. Same engine, half the weight. Thrust-to-weight ratio exceeding 1-to-1 when lightly loaded. In air combat, this made the F-16 a knife fighter turning inside anything in the sky, out-accelerating aircraft twice its size. But for Operation Opera, that thrust-to-weight ratio meant something else entirely. Range, efficiency. The difference between possible and we're swimming home is through Iraqi airspace. The F-16 was the first production fighter to eliminate mechanical linkages entirely. No cables connecting stick to control surfaces. It's just for digital computers interpreting pilot inputs, adjusting hydraulics, making split-second corrections. Combined with relaxed static stability center of gravity positioned behind the center of lift, This created an aircraft that was aerodynamically unstable without computer assistance. Left alone, it would tumble from the sky. But with computers, devastatingly maneuverable, side stick controller mounted on the right console instead of between the legs, reclined seat at 30 degrees to increase GA tolerance. Every design choice optimized for air superiority combat, except none of that mattered for this mission. What mattered was this. The F-16's computers could hold stable flight at 100 feet above the desert for 3 hours straight, while the pilot focused on navigation, fuel management, and not flying into a sand dune at 420 knots. In older fighters with mechanical controls, that kind of sustained low-altitude flight was physically exhausting. Pilots fought constant turbulence, made endless tiny corrections, burned through mental and physical reserves in minutes. The F-16 automated stability, which meant pilots could focus on staying alive instead of staying airborne. Here's the problem that almost killed this mission before it started. Internal fuel capacity, 7,000 pounds. Combat radius, approximately 300 nautical miles. Distance to Baghdad and back, 1,100 miles. The math doesn't work, not even close. So they added external tanks, 2 370-gallon wing tanks, 1 300-gallon centerline tank. Total fuel load, approximately 14,000 pounds. Better, still not enough. Because here's what the aerodynamics textbooks say about low-altitude flight. Air density at sea level is exponentially higher than at 30,000 feet. Drag increases with the square of velocity. Engine efficiency decreases in dense air. At low altitude, the F-16's fuel consumption approaches TWICE, its high-altitude cruise rate. Mission planners calculated they'd need to maintain 420 knots fast enough to cover distance, slow enough not to hemorrhage fuel while staying below 500 feet for most of the transit. At that speed and altitude, the F-16 burns fuel at rates the aircraft manual categorizes as not recommended for extended operations. They were planning a 3-hour mission in a flight regime explicitly advised against for more than 30 minutes. July 1980, Israel receives its first F-16s under the Peace Marble program. June 1981, fewer than 20 aircraft in inventory. Most pilots with less than a year on type. They were selecting an aircraft they'd barely learned to fly for a mission that pushed every performance parameter past redline. But consider the alternatives. F for Phantom. Larger radar cross-section. Worse fuel consumption. Less precision bombing capability. F-15 Eagle. Exceptional aircraft. Twin engines burning fuel at twice the F-16's rate. Airframe optimized for air superiority, not ground attack. K for Israeli designed. Good aircraft. Shorter range than the F-16. The F-16 wasn't the best fighter Israel operated. It was the only fighter that could fly 1,100 miles on internal and external fuel, deliver precision weapons, and return with enough fuel in the tanks to land instead of eject. Maybe. The pre-mission fuel calculations came back with a single-word assessment. Marginal, 8 pilots, 8 aircraft. Fuel reserves measured in minutes instead of hours, and a target that Israel would only get one chance to destroy. 16 Mark 84 2,000-pound general-purpose bombs, 32,000 pounds of tritonal high explosive, all focused on a target the size of a basketball court. This wasn't overkill. This was engineering. The Mark 84 represented decades of refinement in conventional explosives. Hardened steel body, approximately 1 inch thick. 945 pounds of tritonal TNT mixed with aluminum powder for 20% more blast effect. Length to diameter ratio optimized for ballistic stability. Conical nose. Tail fin assembly providing enough surface area to keep the weapon-oriented nose forward through release, flight, and impact. No guidance systems, no laser designators, no GPS. Just physics, trajectory calculations, and pilot skill. But here's the critical component most people miss. The fuse. Standard instantaneous fuses detonate on contact. Hit the reactor dome, explode on the surface, create a spectacular crater. Leave the reactor core potentially intact beneath layers of rubble. The Mark 84s carried delayed fuses, except for 0.4 seconds after impact. At 600 feet per second impact velocity, 0.4 seconds equals approximately 240 feet of penetration, through concrete, through rebar, through structural supports. The bomb doesn't explode until it's inside the target, its blast energy directed inward against the reactor vessel instead of upward into atmosphere. 5 feet of reinforced concrete, It's designed to contain a nuclear accident. Against a delayed fuse Mark 84, it was tissue paper. Now here's where the F-16 separated itself from every other fighter in Israel's inventory. The AN/APQ-66 pulse Doppler radar integrated with a continuously computed impact point system. Feeded aircraft position from inertial navigation, velocity and acceleration from air data sensors, altitude from radar altimeter, target coordinates pre-programmed before takeoff. The computer calculates in real time where the bomb will impact given current aircraft state, displays it on the heads-up display as a symbol overlaid on the real world. This means the pilot doesn't need to fly a perfect wings-level dive. He can maneuver, evade defensive fire, adjust for wind. The computer recalculates constantly, showing exactly where the weapon will go. Stabilize for 2 seconds at release. Pickle the bombs. Pull 7 gigaseconds getting the hell out. The F-15 in 1981 couldn't do this. An APG-63 radar was optimized for air-to-air, credible at tracking fighters at 50 miles, nearly useless for precision ground attack. The F-4 Phantom required manual bombing tables, predictable dive profiles, significantly more time over target time these pilots wouldn't have. The F-16's weapons computer gave each bomb a probability of hitting within lethal radius that exceeded 80%. 16 bombs, 80% hit probability, expected result, 12 to 13 direct hits on a 90-foot dome. More than enough to guarantee complete destruction. Mission planners considered using F-15s. They could carry bombs. They had the range with conformal tanks. But 6 F-15s meant 12 bombs instead of 16. Lower hit probability due to less sophisticated weapons delivery. And splitting the strike package between 2 aircraft types complicated fuel management unnecessarily. They needed overwhelming force in a single wave. No second chances, no follow-up strikes. Because once this happened, Iraq would disperse its nuclear program into hardened bunkers scattered across the country. Facilities Israel's intelligence might never locate. One mission, one target, absolute destruction required. 8 F-16s, 16 Mark 84s, delayed fuses. The engineering analysis said it would work. They were about to find out if the analysis was correct. 1,100 miles to Baghdad, 1,100 miles back, through some of the most hostile airspace in the world. Without aerial refueling, without backup options, the route planning for Operation Opera wasn't just navigation. It was threading a needle through gaps in radar coverage that Israeli intelligence had spent years mapping. The formation launched south from Etzion, chosen because it provided the shortest overwater route during departure, crossed the Gulf of Aqaba, over water void, triggering Jordanian early warning radars during the most vulnerable phase, when 8 fuel-heavy F-16s were climbing to cruise altitude, hit the Saudi coast, turned southeast. Now the real navigation problem began. Saudi Arabia in 1981 operated air defense radar oriented, primarily toward to threat axes. Yemen, to the south ongoing border tensions, occasional incursions. Persian Gulf to the east potential Iranian threats after the revolution. The Western Desert? Desolate, empty, low priority for radar coverage. More critically, the Royal Saudi Air Force and Army Air Defense Forces operated separate radar networks that didn't share data. Coverage gaps? No integration. No coordinated detection picture. Israeli intelligence had mapped these gaps with the precision of cartographers surveying coastline. Every radar site, every coverage pattern, every shift rotation. The route threaded between Saudi radar installations like a surgeon's scalpel, close enough to be efficient, far enough to stay invisible. But staying invisible required more than route planning. It required flying so low that radar physics made detection impossible. Radar waves travel in straight lines. They don't bend around Earth's curvature. A ground-based radar searching for aircraft has a detection horizon determined by geometry, not power. At 100 feet altitude, the radar horizon is approximately 12 miles, meaning the F-16s remained invisible until they were almost directly overhead of radar installations. But flying at 100 feet over the desert for 3 hours isn't just difficult. It's a sustained exercise in precision flying where one mistake puts you into the ground at 420 knots. Desert terrain flat in photographs, deceptively variable in reality. Dry wadies, cutting unexpected valleys. rock formations rising without warning. Elevation changes that don't show up on 1981 Neuramaps until you're too close to avoid them. Heat shimmer at midday, creating optical distortions. Dust reducing visibility. Air density variations making altitude reference difficult. The F-16's fly-by-wire system made this survivable. Computers automatically damping turbulence. Maintaining stable flight without constant pilot input. Previous generation fighters required pilots to fight the aircraft continuously at low altitude. Physically exhausting, mentally draining, increasing the risk of controlled flight into terrain with every passing minute. The F-16 automated stability, which meant pilots could focus on navigation, fuel management, and the mission instead of basic flight control. Each F-16 carried an inertial navigation system measuring acceleration in 3 axes. Integrating those measurements over time to calculate position, state-of-the-art for 1981, also fundamentally limited by physics. INA systems accumulate error at approximately 1 nautical mile per hour of flight. After 3 hours, position uncertainty could exceed 3 miles in any direction. Miss the target area by 3 miles, and you've just flown 1,100 miles to bomb empty desert. So pilots used visual checkpoints, distinctive terrain features selected during mission planning, identifiable even at 100 feet altitude, used to update navigation systems and correct accumulated errors. A wadi intersection here, a rock formation there, an abandoned structure visible against flat sand. Dead reckoning backed by visual confirmation. The navigation technique of explorers and bomber crews, still the most reliable method when GPS doesn't exist, and 3-mile errors mean mission failure. The formation crossed into Iraqi airspace northwest of the H-3 complex, 3 separate airfields serving as Iraq's westernmost air defense installation. Timing calculated for mid-forenoon. Heat and visibility conditions that made defensive combat air patrols less effective. Period of minimal Iraqi air activity based on months of intelligence collection. Then northeast toward Baghdad. Following terrain that masked them from Iraqi early warning radars, positioned to detect threats from Iran to the east. This routing added distance, burned more fuel, but reduced detection probability enough to justify the cost. Every decision balanced competing factors. Speed versus fuel consumption. Direct route versus radar avoidance. Risk versus probability. Mission planners optimizing for survival, not efficiency. And throughout this entire transit, 6 F-15A Eagles flew escort. It's not carrying bombs, full air-to-air loadout. 4 AIM-7 Sparrow radar-guided missiles. 4 AIM-9 Sidewinder infrared missiles. Their job, positioned between any Iraqi response and the strike package, used superior speed and climb rate to intercept threats before they endangered the bomb-laden F-16s. The APG-63 radar optimized for tracking airborne targets, providing early warning of Iraqi interceptors scrambling to respond. But here's what's remarkable. The F-15s never fired a shot. The Iraqi air defenses never detected the formation until they were already climbing to attack altitude over the target. 1,100 miles of hostile airspace. Crossed undetected. The route planning had worked. Now came the hard part. Late afternoon, sun angle approximately 20 degrees above the horizon looking west. Not coincidental. Defenders looking toward the sound of approaching jets would be staring directly into the sun. Visual acquisition, nearly impossible. Shift change at the reactor facility. French technicians and Iraqi workers rotating positions. Minimum personnel exposure calculated to the quarter hour. And the formation, having flown 3 hours at 100 feet, burning fuel at rates the aircraft manual explicitly warned against climbing. Low altitude to medium altitude, approximately 2,000 feet above ground level. This was the transition. It's the moment of maximum vulnerability. Because climbing to attack altitude meant exposing themselves to ground-based air defenses, giving Iraqi radar their first clear detection of the inbound strike. But weapons delivery accuracy required altitude. The Mark 84s needed to be dropped in a 30-degree dive profile, sufficient ballistic trajectory, enough time for pilots to acquire the target visually, stabilize the dive, release at correct airspeed and altitude. You can't execute precision bombing from 100 feet, so they climbed. And Iraqi air defenses finally saw them. Inside the cockpit, the heads-up display showed the target coordinates overlaid on the real world. The weapons delivery computer processing inputs. Aircraft position from INS. Velocity from air data sensors. Altitude from radar altimeter. Target coordinates pre-programmed before takeoff. Wind velocity. Air density. Bomb ballistics. Calculating continuously in real time where the weapon would impact given current aircraft state. Displayed as a small symbol on the HUD. Move the aircraft. The symbol moves. The computer recalculating impact point 30 times per second.
Wow.
This was the technological advantage that made the mission possible. The pilot didn't need to fly a perfect dive. He could maneuver, adjust for defensive fire, compensate for wind. Just keep the computed impact point near the target, stabilize briefly at release, pickle both weapons, then get out. Individual runs, not formation attack, spaced approximately 10 seconds apart. This served multiple purposes, prevented mutual interference between aircraft, distributed the attack over 90 seconds instead of concentrating in a few seconds, created cumulative structural damage later bombs benefiting from weaknesses created by earlier detonations. First aircraft rolls in from 3,000 feet, accelerates to 450 knots, stabilizes at 30-degree nose-down attitude. Release altitude, 1,000 feet. 2,000 pounds of hardened steel and tritonal separating from wing pylons. Ballistic trajectory, tail fins stabilizing, nose pointed at the reactor dome. Impact velocity, 600 feet per second. The pilot doesn't see the impact. He's already pulled 7 gigaseconds, turning hard, descending back toward low altitude. This team's exceptional maneuverability to present a difficult target for anti-aircraft gunners. Second aircraft rolls in. Through his canopy, he sees the first bomb detonate, dust and concrete fragments erupting upward. The dome cracking, release, pull, egress, third, fourth, fifth. By the 6th aircraft, there's no dome anymore. Just a crater where Iraq's nuclear ambitions used to be. Witnesses on the ground reported the aircraft appeared from nowhere, coming out of the sun, engines roaring. Oh no. Warning until bombs began detonating. Anti-aircraft artillery, 37 millimeters and 57 millimeters, fired streams of shells toward the sky. Without radar guidance, without adequate warning time, gunners firing at where aircraft had been, not where they would be by the time shells reached altitude. Defensive response, minimal and ineffective. 14 bombs struck within the target area. 10 scored direct hits on or immediately adjacent to the reactor dome. 2 missed entirely struck administrative buildings, causing secondary damage. Force of the explosions collapsed the reactor dome completely, destroyed the reactor core, rendered the entire facility irreparable. 1 French engineer killed. 10 Iraqi soldiers at defensive positions, casualties. Critically, no radioactive contamination. The reactor hadn't been loaded with fuel yet. The timing calculations, the urgency that drove this entire operation, validated. Strike it now, and it's a concrete structure filled with conventional explosives. Strike it next month, and it's Chernobyl. Total time over target, 90 seconds. Years of construction, gone. Hundreds of millions of dollars, vaporized. Iraq's public nuclear program, terminated. And 8 F-16s, fuel gauges reading dangerously low, turning for home. The egress route followed the same path in reverse, except now, Iraqi air defenses were fully alert. Saudi Arabia had scrambled F-15s responding to unidentified aircraft transiting their airspace, and the fuel situation had gone from marginal to critical. 3 hours outbound burning fuel at low altitude, 90 seconds over target, now 3 hours back. The F-16As were operating in a regime where fuel reserves were measured in minutes, not hours. Mission planners had calculated this, accepted it, proceeded anyway. But calculations on paper are different from watching fuel gauges drop toward empty while you're still 400 kilometers from friendly airspace. The 6 F-15 Eagles proved their worth during egress, positioning themselves between the strike package and any Iraqi response. Iraqi MiG-21s scrambled from several bases failed to intercept. Formation had already crossed back into Saudi airspace before Iraqi fighters could reach them. Saudi F-15s airborne, searching for the unidentified aircraft that had violated their territory. They never made contact. Whether due to Saudi reluctance to engage or Israeli evasion tactics remains unclear. But the strike package returned to Israeli airspace without firing a shot in air-to-air combat. The F-16s crossed back into Israeli airspace, descended toward Etzion, landing gear down, fuel gauges reading numbers that made ground crews nervous. Several aircraft landed with less than 1,000 pounds of fuel remaining, approximately 10 minutes of flight time. One pilot's engine flamed out on the taxiway. Not in the air, thank God, but close enough that the margin between successful mission and international incident involving crashed F-16 in Saudi Arabia was measured in minutes of fuel burn. The mission had succeeded, not a single Israeli aircraft lost, but they weren't operating with comfortable margins. They were operating in a regime where the aircraft manual literally said flight not recommended. They'd pushed the F-16 beyond its design specifications, beyond what General Dynamics engineers intended, beyond what most fighter pilots would consider sane. And they'd proven that with sufficient planning, acceptance of risk, and minimal fuel margins, even lightweight tactical fighters could accomplish strategic objectives. Iraq and most Arab nations condemned the strike immediately, brought it to the UN Security Council, unanimous condemnation of Israel's actions. France suspended delivery of additional nuclear fuel and components, the Osirak program even, if Iraq attempted reconstruction was finished. But here's what the official reports didn't say. The Begin Doctrine had just been established. Named after Prime Minister Menachem Begin, Israel would act preemptively to prevent hostile states from acquiring nuclear weapons. This doctrine would directly influence Israeli strikes against Syria's Al-Kabor reactor in 2007. Same operational concept, same willingness to violate international law for perceived survival. And it reshaped how the world discussed Iran's nuclear program for the next 4 decades. Here's where it gets complicated. Mission succeeded tactically. Reactor destroyed. No aircraft lost. Surprise achieved. But strategically, Iraq's response was to accelerate and diversify its nuclear program. Moving from one high-profile facility to a distributed network of clandestine sites, harder to monitor, harder to target, operating without international oversight. By the early 1990s, revealed after the Gulf War, Iraq had developed a surprisingly advanced nuclear weapons program. Hidden, underground, far closer to success than Osirak ever got them. Some analysts argue Operation Opera actually accelerated Iraqi nuclear development by demonstrating the vulnerability of centralized facilities, by pushing the program into complete secrecy. Others counter that without Osirak, Iraq would have achieved nuclear capability years earlier. Both arguments are compelling, suggest that military strikes, however tactically brilliant, create strategic outcomes that defy simple cause and effect analysis. One French engineer died in the attack. Diplomatic complications Israel had anticipated but accepted as necessary. Damaged French-Israeli relations for years, contributed to France's subsequent reluctance to provide military technology to Israel. Tactical operations occur within diplomatic contexts. Consequences extend beyond immediate military objectives. Before Osirak, the F-16 was marketed as a lightweight air superiority fighter, affordable complement to the F-15. After Osirak, multi-role strike fighter, equally capable air-to-air and air-to-air ground. This perception shift influenced procurement worldwide. Nations that might have purchased dedicated strike aircraft opted for F-16s instead. The operational flexibility demonstrated at Osirak became a central selling point, contributing to the F-16 becoming the most widely exported Western fighter of its generation. The mission highlighted specific F-16A limitations that drove improvements. Lack of conformal fuel tanks. Later variants added 4,000 pounds capacity without occupying hardpoints. Navigation accuracy over long distances. GPS would eventually eliminate this entirely. Weapons delivery requiring predictable dive profiles, laser and GPS-guided weapons would address this. The mission also established training requirements. Exceptional altitude flying skills, navigation accuracy without GPS, formation discipline across hundreds of miles without radio communication. Lessons that shaped Israeli F-16 training programs and influenced how other air forces approached multi-role fighter training. So did Operation Opera prevent an Iraqi nuclear weapon? Yes. The Osirak reactor never produced a single gram of plutonium, and no. Because Iraq's nuclear program after 1981 went dark, went underground, and by 1991 was this close to success. The paradox. The reactor dome at Osirak destroyed. The nuclear ambitions that built it metastasized. Here's the question that keeps proliferation experts awake. If Osirak, under IAEA safeguards, subject to international inspection, relatively transparent, was actually less dangerous than the covert program that replaced it, then what did the strike actually accomplish? Every bomb that hit the reactor dome was a violation of international law. Every bomb that missed would have been a tactical failure. 8 pilots carrying out an illegal strike. 8 pilots executing what Israel calculated as necessary for survival. The line between preemptive defense and preventive war isn't drawn in legal textbooks. It's drawn at 420 knots, 100 feet over Iraqi desert, by pilots who know the world will judge them either way. The Begin Doctrine suggests Israel will use military force to prevent regional adversaries from acquiring nuclear weapons. But Iran's program is far more dispersed, better defended, more advanced than Iraq's was in 1981. The F-16, despite continuous upgrades, may not be the optimal platform for strikes against deeply buried Iranian facilities. Modern platforms like the F-35, stealth characteristics, penetrating weapons capabilities, the technological evolution driven in part by lessons learned from missions like Osirak. Here's what remains classified. Did destroying what Israel could see prevent the threat Israel couldn't see? Or did it create a more dangerous program hidden from international oversight? Israel bet it would prevent proliferation. Iraq bet it wouldn't stop their ambitions. History suggests they were both right. 8 F-16A Fighting Falcons, barely 2 years in service. A mission that pushed every performance parameter beyond design specifications. Range, extended beyond recommendations. Fuel margins, measured in minutes. Bombing precision, exceeding expectations. They proved that lightweight tactical fighters could execute strategic missions. They validated the F-16's multi-role capabilities. They established precedents that continue shaping Middle Eastern geopolitics. But here's what they couldn't answer. Whether destroying a reactor prevents proliferation, whether tactical success translates to strategic victory, whether some problems exceed even the most capable aircraft's ability to solve, the destroyed reactor at Osirak stands as both a monument to air power's reach, or a reminder of its limitations. Because nuclear technology spreads regardless of military strikes, driven by fundamental scientific knowledge that cannot be bombed out of existence, the F-16 proved itself that day. Flew farther than it should have, hit harder than expected, returned when fuel calculations said maybe. The questions that motivated the mission, still unresolved. 40-plus years later, some problems exceed even the most brilliant engineering.